How do you know if an atom is stable? In this video, we're going to learn about radioactive decay. An atom is composed of subatomic particles called protons, neutrons, and electrons. Positively charged protons.
Can you hear the video? No? Can, okay.
Protons and neutrons with no charge from the central nucleus. Negatively charged electrons orbit the nucleus. For more information on atomic structure, watch this video. A strong nuclear force holds the positive protons and neutral neutrons together in the nucleus, and is what determines if a nucleus is stable. In stable nuclei, the force is strong enough and brings sufficient energy to hold the nucleus together permanently. Most of the nuclei formed during the Big Bang nearly 14 billion years ago are still in existence today.
So what is the age of the atoms in your body, guys? Satish? 14 billion years ago.
But not all nuclei are stable. Unstable nuclei either have too many protons or too many neutrons, upsetting the strong nuclear forces. Unstable nuclei try to balance themselves by giving off the excess proton or neutron. This is radioactive decay. Unstable nuclei are radioactive and emit radiation. There are three types of decay: alpha decay, beta decay minus, or beta decay plus.
Okay, you don't learn beta decay plus, guys. Yours is only alpha decay, beta decay, which is negative, and you learn gamma radiations only. So you learn only three types of radiation: alpha, beta, gamma. Later, when I teach you fission, you will learn the neutron decay also. So there's another one, neutron.
Alpha decay is the loss of an alpha particle. An alpha particle is made of two neutrons and two protons. They have a mass of 4 and a charge of +2. When an atom loses an alpha particle, the mass number decreases by 4 and the atomic number decreases by 2. A new element is formed that is 2 places lower in the periodic table. When an isotope has too many neutrons, it decays by beta minus decay. A neutron changes into a proton and an electron. The proton is retained by the atom, while the electron is lost. The lost electron is high energy and is called a beta particle. By losing a neutron whilst gaining a proton, the mass number of the atom remains the same, but the atomic number increases by 1. A new element is formed that is 1 place higher in the periodic table. When an isotope has too many protons, it decays by beta plus decay. A proton is converted into a neutron and a positive beta particle called a positron.
Positron is not in your syllabus, so you don't have to look at this part.
Teacher.
Positrons have the same.
There
are people joining in.
Okay, hold on. Okay, all are in a day. Okay. All right, no more people in, Okay, should I replay the video? Start from beginning again? Hello? Hello? Guys? Can you all hear me?
Yes.
I start from beginning again,
How do you know if an atom is stable? In this video, we're going to learn about radioactive decay. An atom is composed of subatomic particles called protons, neutrons, and electrons. Positively charged protons and neutrons with no charge from the central nucleus. Negatively charged electrons orbit the nucleus. For more information on atomic structure, watch this video. A strong nuclear force holds the positive protons and neutral neutrons together in the nucleus, and is what determines if a nucleus is stable. In stable nuclei, the force is strong enough and brings sufficient energy to hold the nucleus together permanently. Most of the nuclei formed during the Big Bang nearly 14 billion years ago are still in existence today. But not all nuclei are stable. Unstable nuclei either have too many protons or too many neutrons, upsetting the strong nuclear forces. Unstable nuclei try to balance themselves by giving off the excess proton or neutron. This is radioactive decay. Unstable nuclei are radioactive and emit radiation. There are three types of decay: alpha decay, beta decay minus, or beta decay plus. Alpha decay is the loss of an alpha particle. An alpha particle is made of two neutrons and two protons. They have a mass of 4 and a charge of +2. When an atom loses an alpha particle, the mass number decreases by 4 and the atomic number decreases by 2. A new element is formed that is 2 places lower in the periodic table. When an isotope has too many neutrons, it decays by beta minus decay. A neutron changes into a proton and an electron. The proton is retained by the atom, while the electron is lost. The lost electron is high energy and is called a beta particle. By losing a neutron whilst gaining a proton, the mass number of the atom remains the same, but the atomic number increases by 1. A new element is formed that is 1 place higher in the periodic table. When an isotope has too many protons, it decays by beta plus decay. A proton is converted into a neutron and a positive beta particle called a positron.
As I said earlier, we don't learn the positive beta decay. We only learn the negative beta decay. We only learn the negative beta decay, right?
Positrons have the same mass as electrons, but the opposite charge. By losing a proton but gaining a neutron means the mass number stays the same. But the loss of a proton means the atomic number decreases by 1. So how do we know if an atom is stable or unstable? We can determine whether a radioisotope is likely to decay and what type of decay is likely to occur by looking at its position on a proton-neutron NZ graph. This graph shows the number of protons on the x-axis and the number of neutrons on the y-axis. This is the stability line. If a radioisotope lies left or right of this line, it is unstable and likely to decay to become stable. A radioisotope that lies to the left of the stability line has too many neutrons and is likely to undergo beta minus decay, so give off electrons. A radioisotope that lies to the right of the stability line has too many protons and is likely to undergo beta plus decay, so give off positrons. If particles have a high number of protons, usually more than 82, they are likely to undergo alpha decay. In this video, we have learned that unstable nuclei either have too many protons or too many neutrons, which upsets the strong nuclear force holding the atom together. Unstable nuclei try to balance themselves by giving off the excess proton or neutron either through alpha, beta minus, or beta plus decay.
If you liked the video, give it a thumbs up and don't
Okay, done with the video. I got one more to explain to you all. Alpha, beta, and gamma radiations. Okay.
We saw in the last video that each element
Listen
comes
carefully,
in a
huh?
number of different forms, called isotopes, each of which has the same number of protons, but a different number of neutrons. Importantly though, only one or two of an element's isotopes are stable, while the rest of them are unstable, and so can undergo radioactive decay, which is where they emit something so that they can change slightly and become more stable. So when we say that a material is radioactive, all we mean is that it consists of unstable isotopes that can decay. In this video, we're going to take a closer look at the four types of nuclear radiation, namely alpha particles, beta particles, gamma rays, and neutrons. And we'll cover how ionizing and how penetrating each of them are. Let's start with alpha radiation. Alpha particles are made up of 2 protons and 2 neutrons, which is exactly the same as the nucleus of a helium atom. So we normally represent alpha particles with helium's nuclear symbol, He. Importantly though, alpha particles don't have any electrons, so they have an overall charge of 2+ from those 2 positive protons. Because they are relatively large, alpha particles are easily stopped by collisions with other molecules, which means that they can't penetrate very far into other materials. In fact, they can only travel a few centimeters in the air, and are absorbed by a single sheet of paper. However, their large size and their strong charge does make them very strongly ionizing, which just means they can easily knock electrons off any atoms that they collide with. Next up, we have beta particles, which are just electrons. So they have a charge of -1 and virtually no mass. Now, the weird thing is that electrons aren't emitted from one of the atom's shells. Instead, one of the atom's neutrons decays into a proton and an electron. The proton stays in the nucleus, but the electron is emitted out at high speed. Because beta particles are pretty tiny, they are moderately ionizing, and they penetrate moderately far into materials. For example, it would take several meters of air, or about 5 millimeters of aluminium to stop them. Now, gamma rays aren't particles at all. They're actually waves of electromagnetic radiation, like light is. And they're often emitted after alpha or beta radiation, as a way of the nucleus getting rid of a bit of extra energy. As they don't have any mass or charge, they tend to pass straight through materials, rather than colliding with any of the atoms, which makes them only weakly ionizing. This means that they can penetrate really far into materials before being stopped, so it can travel long distances through air, and it takes thick sheets of lead, or multiple meters of concrete to stop them. The last type of radiation we need to look at is the emission of a neutron, and there really isn't much to know. If a nucleus contains too many neutrons, which is making it unstable, it can just throw out a neutron to increase its stability. So to quickly recap, alpha particles are made up of 2 protons and 2 neutrons, and will be stopped by a single sheet of paper. Beta particles are just an electron, and can be stopped by a thin sheet of aluminium. And gamma rays are electromagnetic waves, which require a thick piece of lead to stop them. That's everything for this video though.
Okay, done.
So if you
With
found
the
it
video, we go
useful,
back to our notes. Let's check our notes. Okay. Okay, we have finished the page 1, we finished already. Page 2 also finished already. Okay, when we talk about page 3 just now, all right, did I explain to you all page 3 or not, guys? Hello? Cheng? Done already,
Done
page
already.
3 done. Okay, just a recap of page 3. Just now we saw the video. Okay, what's happening here? First alpha, it's the nucleus of helium. So write alpha as He42, right? Positive 2 charge. Mass is big. It can move almost like 10% speed of light. Ionization strength is very strong. Very strong.
I
Huh?
thought finish already.
Okay, and then, yeah, I'm just recapping.
Oh, okay.
And then penetrating power, very weak. Very weak. So it's very difficult to penetrate through any medium. Deflection electric field, sedikit, very slightly. Magnetic field also slightly. The range in the air is a few centimeters only. Beta symbol, it's beta, so it's electron, 0, -1, beta. High-speed electron from the nucleus, charge is -1. Mass is very small, almost none. Can move up to 90% speed of light. Ionization strength is medium. Okay, medium. It's not so strong like alpha, but less than alpha. Penetrating power also medium, better than alpha. Better than alpha. And then deflection electric field is great because as electrons are flying through in air, it's actually current. It's actually current, you know. So once they're moving, they're actually creating current. Deflection electric field also very strong. The range, a few meters. They can move a few meters in air depending to the source. I told you last class, depending on the source. The source is a very strong source. They can move a further distance. And depending to the substance or the elements, based on the elements, see what is the amount of emission. I told you last week, how long, how much. Okay. What is the time of exposure, how long you're exposed to it. And number 2 is, we must see what is the intensity of exposure, right? Then we have gamma ray. This is typing error. Gamma ray, it's an electromagnetic wave. Gamma ray. Gamma, okay, neutral because it's an electromagnetic wave. No mass, but speed of light. Very dangerous. Ionization strength, weakest. Very weak, like almost none. Weak, like almost none. Penetrating power, this is the strongest. This is the strongest of all. Strongest, very strong. You saw the video also just now, you could know. And deflection in magnetic electric field is none. The range in the air can move up to kilometers, right? Okay, now, today we're supposed to look at the detectors to detect radiation. But before I go to that part, let me talk about the decay part, because since you saw the 2 videos, you'll get the picture clearer now. Okay, see here, radioactive decay is a spontaneous, random process, so nobody can stop it. We don't have any technology like physical pressure, chemical, nothing we can do. When one atom is discovered to be radioactive, this atom remain as a radioactive element and it will decay on its own naturally. Nothing can be done. Clear? To just decay. We can only hold and protect us from we can contain the radiation only. Okay. How alpha decay will occur? Okay, see, if let's say you are given one element with a nucleon number of 100 and proton number of 50, example. As this element decay and releases alpha. Alpha we write as 4,2 helium. This is alpha, all right? So the remaining new, and of course energy will come out, all right? The energy can be in the form of gamma ray heat, all right? That's energy. The remaining element now, the new element formed after the first decay of releasing helium, will have a nucleon number of 96 and proton number of 48, because 48 plus 2, you get back 50. 96 plus 4, you get back 100. Any question? Any question? Okay. And a beta decay. If I have a beta decay, let's say the original element is having a 40 nucleon number, and 18 proton number. 40 nucleon number, 18 proton number. See carefully. It is forming a new element, and by releasing one single beta, okay? This is one single beta element, and of course, while decaying, they will release energy. So what happened? This element is going through a decay process. It is also releasing energy and releasing one single beta. So what happened to the nuclear number? The nuclear number remained the same. To get back 18, we have 19 here. So 19 minus 1, you get back 18. So every time when the nucleus decay, they will form back extra one proton. All right, remember just now in the video, one neutron split to form one proton and one high-speed electron called beta. The high-speed electron called beta will come out from the nucleus and move to the air outside of the atom. But the proton which just came from a newborn proton from the neutron will remain in the nucleus. That's why initially there were 18 protons, one of the neutron pecah, so you get additional one proton, and this is how your equation look like. Any question? Any question, guys? Okay, next, gamma decay. Gamma decay, you must understand that when a gamma decay occurs, this is the original element. Let's say it's having 200 nuclear number, 96 proton number. As it decay and only release gamma ray. Let's say it's only releasing gamma ray. You will see that the element remain the same. The element remain the same. What is the difference between these two elements? The difference will be before the decay process, it has a higher energy. It has a higher energy before the decay, and after the decay, it will have a lower energy, low energy. That's all. That's all. This is how the decay will occur. So I repeat again, whenever there is a alpha decay, you just look at the nucleon number. The nucleon number will decrease by 4 if one alpha is coming out, one alpha. The proton number will decrease by 2 if one alpha is coming out. All right? And for sure, they will release energy. And then look at the beta decay. The beta decay, if you look at it carefully, all right, the nucleon number will remain the same if one beta element is emitted. The proton number before and after increase by 1. So the idea is to balance the number of proton before and after. Before was 18, after also still 18. See, 19 minus 1 is still 18. That's how we look at the beta decay. All right? Then the gamma decay, very simple. The gamma decay, it's remain the same. The nucleon number and the proton number remain the same. Any question, guys? Anyone? Any question? Jaden?
Yes, sir.
Any question?
I think Marcus got a question, Asha.
What, Marcus?
May I go to the toilet, please? I got no question.
Can. You take your card first, huh? Okay, now see here, all of you are. Okay, now. Okay, pass. Okay, see here. Now let's say you have, for example, carbon, all right, 14. Carbon 14. Carbon 14 found to have 6 proton number. Carbon 14 going through a beta decay. I'm explaining about beta decay. Beta decay. Right? Beta decay. Carbon 14 will emit one beta. One beta. This is beta. And of course, emitting energy. Energy is coming out, right? So what is the new product? The new product must have 7 proton number and nucleon number remain the same. It found to be nitrogen. So whenever carbon-14 decay by emitting 1 beta particle, the remaining element, the new element formed after the decay process, is a new atom of nitrogen. Nitrogen. So this is the idea. This is the idea, okay? Beta decay, right? Then let's say now, see here carefully now, you have one element Q with 100 nucleon number, 52 proton number. This element releases 4 alpha and 2 beta, and of course energy, energy. Okay, and energy, right? Energy is released. Okay, now the new element formed is R. What should be the nucleon number and what should be the proton number of element R? So initial element was Q with a nucleon number of 100 and proton number of 52. All right. This element is decaying by releasing 2 alpha and 2 beta. So what should be the new element which is formed? What is the nucleon number and what is the proton number? What is the nucleon number and what is the proton number of the new element formed? So what we do here, we take the nucleon number first. 100 is equal to A plus 4 times 4 plus 2 times 0. So A equals to what, class, faster? Berapa? A equals to what, Satish? A equals to what?
84.
84. So A is 84. So A is 84. A is 84. So what is the value of B? Yongsin, what is the value of B? How to calculate B now? Same mechanism, same method only. So what we do? We take 52. 52 equals to B plus 4 times 2 plus 2 times minus 1. Yongsin, what is B? 8 minus 2, 6. 52 minus 6, what we get? 46, that's B. Correct, right? 4 times 2 is 8, 8 minus 2 is 6, so bring the other side, 52 minus 6 is 46. Yes, correct. So, the value for B is 46. Siapa ada soalan? Any question? Anyone? Any question, guys? No? Okay, kalau tak ada, we move on. Go back to the notes. Okay, so today we look at radioactive decay, right? Okay, one more question later to that. Wait, okay, see here. Complete the equation, all right, to show the emission of alpha particle. Okay, let's show the alpha particle emission. So this is 210,206. So 4, 2. 84 minus 82, 2. So you get your alpha. Get your alpha plus energy. So this is how we show the emission of alpha particle. All right. So this is the equation. You see a bigger equation is the down one. See, uranium plus neutron, you get krypton, barium, and 3 neutrons. So let's look at this later. Okay, I think there's one more equation. This one is fusion. Okay. Look at here. Okay. Yeah, this one. See here. nuclear reaction uranium-235 is bombarded by neutron, giving caesium or cesium, rubidium, and 2 neutrons. Energies from the table determine the energy release when one uranium-235 undergoes such a reaction. So first you will have uranium-235. Uranium-235 is 92, guys, 92, right? It is forming cesium 141, all right, plus rubidium 93 plus 2 neutrons. Neutrons, you must put 1 and 0, all right, okay, and energy, all right, energy. So look at this. If you find the proton number of rubidium, proton number of cesium, you balance up and see, you must get 92. And this is how we write the equation, all right? So this is how we explain radioactive decay equation. Radioactive decay equation. So I repeat again, see here. Okay, see here carefully. Let's say now you are given one element P, all right, with a nucleon number 94, proton number 46. Okay, this element forms a new element Q with nucleon number A, proton number B, and it releases 2 alpha helium and energy. So what is A, what is B? Marcus, try. Marcus, you came back from toilet today?
Yeah.
Yeah, okay. Try
Trying.
A, Marcus. How many, Marcus?
Is it 86?
86, yes, correct. So A is 86. So what is B, Marcus?
$42.
Yep, that's it. Okay, good. Okay, I hope all of you can understand this. Anyone got any question? Anyone got any question or not? Okay, other question. Kalau we go and look at, right, the devices or the radiation detectors. Okay, the first one we're going to look at here is what we call as cloud chamber. Okay, we call this cloud chamber. Cloud chamber, later you can Google and see the videos, got YouTube, got videos all. Okay, cloud chamber is made up of few components. At the bottom here got sponge. Then we put solid carbon dioxide on top of it. Then the whole thing is pressed with a black metal plate. It's pressed with a black metal plate. This is a black metal plate, right? Okay. Then we will bring in the radioactive source, and on top here we have a transparent perspex to see through. We can see through here. See this, the size can be like a rice cooker size, you know, a medium rice cooker size, right? Okay. And then at the side here, see carefully. Okay, we have this felt pad saturated with alcohol. Saturated with alcohol. This is how a cloud chamber look like. Okay. The whole objective of having the solid carbon dioxide and the alcohol is to create vapor inside here. To create vapor inside here, a thick vapor like a mist. Like a mist. So when you see from on top here, the transparent window on top here, inside here you look like a carbos, like a mist, you know, it's like a totally like a mist. So solid carbon dioxide will bring down the temperature. So first thing what happened, temperature inside the cloud chamber decreases. all right? And solid carbon dioxide, bless you, solid carbon dioxide will undergo sublimation. So from solid, it straight change to gas. So inside here, you have a lot of carbon dioxide and alcohol. Alcohol vaporize. Alcohol will vaporize. So what happened here is that inside here, you will get like a thick white color mist. Thick white color mist. And if you watch some YouTube videos, they will shine inside with a certain green color light just to make it refraction and can look at a thick observation inside. So the whole idea here is that inside the cloud chamber, when you see from on top, inside the cloud chamber, when you see from on top, okay, the whole idea here is that when you see from on top here, inside the cloud chamber, there'll be like a very thick mist. Any question? Okay, now, see, alcohol, vapor, condense, right? You get thick vapor, and the alcohol vapor is saturated because of the dry ice. So here you get a very thick one. Okay, now what happens? See carefully. When you see from on top here, all right, if you still don't get the idea what I'm trying to tell you all, okay, early morning after you mandi, your window, your mirror in your bathroom, right? If let's say the vapor is too strong, you mandi pagi kan, the vapor too strong, you'll get the mist one, then you can put your fingers and just cross like that, you'll get lines there. This is called a track. So what happened here exactly is that you see through the cloud chamber window on top here, right? From here, when you see through from here, all right, when you see through from here you see like a thick man-made cloud mist there, and as you bring the radioactive source inside here, you're going to see lines of tracks. Based on the lines of tracks, we are able to determine whether what is inside there is alpha radiation, beta radiation, or gamma radiation. You see here carefully, okay. If let's say we place inside here the radioactive element, all right, it's here, and if let's say it is emitting alpha, so the alpha tracks will be released as a thick track. These are the alpha tracks. They are released as thick tracks, all right? So when you see through, you will see from the cloud chamber window on top there, a very thick track in between the mist. So we know for sure this is alpha track. And if let's say it's a beta track, what happened here is that the source is here. You place the source here, you'll see a tiny wavy tracks there. So this is the beta track. So we can differentiate whether it's alpha or beta tracks. So as the radiation is placed inside, the radioactive element is placed inside here, we can see the tracks in it. Once you get a very thick track, you know it's alpha. Very thick tracks, you know it's alpha. If it's a wavy one, you know it's a beta track. And finally, if it is a gamma track, if gamma is coming out here, right, very unclear small wave there. Very unclear small wave. Any question? Who got question? Anyone got question? No?
No.
No, So based on this, let's say now if I give you an idea, see, now let's say you are using a cloud chamber, right? And you are seeing from on top. When you see from on top, as you use a cloud chamber, this is a cloud chamber, you are seeing through the perspex window. As you place the radioactive element here, your specimen is here, what you see from here is clear, thick track, clear, very thick track, and a small wavy track, a very small wavy track, okay? So you will know for sure this substance, the substance that we were using actually was emitting alpha and beta. Do you understand now? Do you understand? Sandra, do you understand?
How to see if there is gamma? Leh?
Gamma can see if, let's say now, let's say the substance you place inside it, right? Okay, this substance is not emitting anything, but you can see like small wave, that tiny, confirm is only gamma. Lah. But most of the cases, alpha and beta are very clear, very clear. Gamma very difficult to see. Clear?
Yeah.
Okay, now what happened? See, listen carefully. Okay, you listen carefully. Okay, based on the radiation released here, you are only able to detect what type of radiation, that's all. You are only able to detect what type of radiation, that's all. You cannot actually determine the quantity. Quantity you won't know. So you cannot count, you cannot measure the amount. That one cannot. You only know, okay, this substance is releasing alpha, beta, and gamma radiation, that's all. Or combination of alpha and beta, or combination of beta and gamma. You are not able to understand that the quantity, because we can actually measure radiation by using the Serviette count or the Becquerel count. So here you can't use the Serviette count to understand what is the quantity it was emitted. You cannot do that. Clear? Okay. So first device was cloud chamber. Second device is the dosimeter. This is a very high-tech, simple device. Okay, it's a radiation dosimeter. You can even check in Lazada, they are selling. You can buy if you want to. All right. So it's a very simple mechanism. There's a detector front here. So the detector will tell you the count amount. That's also a very simple one. All right. Okay. Beside that, the most accurate is the Geiger-Müller. The most accurate is the Geiger-Müller. Geiger-Müller is very important because we will know the actual amount of radiation. If you use Geiger-Müller, you know actual amount of radiation. We can count the radiation by count per second or count per minute. The amount can be calculated by count per second or count per minute. So this is a bit expensive device. As I told you in the last class, I don't know if I mentioned to you or not, we are not allowed to keep all this in the school. So the school lab won't have anything. Don't worry. Only dosimeter, if I want to buy, I can bring. That's all. Because why? The reason is very simple. Schools up to our level are not allowed to carry any radioactive substance at all. Dangerous for kids like you. And with kids like Yi Cheng, Marcus, we cannot keep them around us at all. Understand, guys? Okay. How a Geiger-Müller work? Okay, before how a Geiger-Müller work, I want to go back to the cloud chamber. Okay. Kalok, are you there?
Yeah.
Yeah, okay. What is the purpose of this alcohol? This solid carbon dioxide. The purpose of solid carbon dioxide?
Lower down the temperature.
Yes, to lower down the temperature. So by using the solid carbon dioxide, we can create a very low temperature inside here. All right. And the alcohol vaporized or saturated, we get a thick mist inside here. So as we see from on top, we get a clear picture of the tracks. Any question, guys? Anyone got any question? Okay. Geiger-Müller. All right. Geiger-Müller. Okay. See here. It is actually made of, if you see carefully here, it's made of, right, a central wire. See here, central wire, a positive electrode. So it's connected to the positive terminal. The central wire is a positive electrode. Okay. The positive electrode, central wire. Okay. It's connected to a positive terminal, central wire. Then the body is made of aluminum. This body is made of aluminum tube, and it's connected to the cathode. So remember just now, alpha positive charge, beta negative charge, right? So when the radioactive element emission as it enter, the positive charge of alpha is discharged by the negative electrodes. the positive charge of alpha is discharged by the negative electrode, and the negative beta is discharged by the central wire. Central wire will discharge the negative beta alpha by the aluminum tube. And inside got helium, neon, and argon gas at low pressure. Did you notice all these three are inert gases and they're supposed to remain neutral, remember? But the presence of gamma ray with the very high frequency, it will temporarily, for temporary moment, not for very long, temporarily, for a very short moment, it will actually ionize this for a while. So as they are ionized, we realize ions are formed inside here around the central wire. They will be discharged, and as the high voltage flow here, the scale meter will have transistor. The transistor will amplify the current. So we know basically the system works in a very simple way. When the ions are discharged, remember, as the ions are discharged inside the Geiger-Müller tube. When the ions are discharged inside the Geiger-Müller tube, see here, inside here, when the ions are discharged inside here, it can be very tiny amount of discharge, but with the help of the transistor inside the rate counter, we will amplify the current, and it is calculating number of time current flows. Number of time current flows per second or per minute. That's how we get the count per second or count per minute. How do we get the count per second or count per minute? We are looking at the number of time current flows in the circuit. As the number of time current flows in the circuit, we will know that what is the quantity of discharge which is detected. What is the quantity of discharge which is detected? All right. So the scale meter here will tell us, will show us what is the number of time the current flows in the circuit. All right. So now one simple question. Okay, let's call Jaden. Jaden?
Yes.
Okay, now I have substance A, substance A, substance B. Substance A emitting 500 counts of emission per second. Substance B emitting 500 counts of emission per minute. Count per second, count per minute. Between A and B, which one you think a stronger radioactive element?
A.
A, definitely A, because it's emitting 500 counts in 1 second. That means in 1 minute, it's going to emit almost 30,000, correct, right? Yeah. 330,000 counts per minute. That's how. So A is actually a stronger emission. All right. Any question, anyone? Anyone? Any question? So we have looked at first cloud chamber. We have looked at cloud chamber. How does it work? We try to understand the component of cloud chamber. You must know. You must know the component of cloud chamber. And you know when you send through, when you place the radioactive element, this is the radioactive element inside the cloud chamber, you can see the type of radiation. Okay, based on the tracks, you can identify which radiation was emitted. All right, and then dosimeter is a simple device. It's not so high-tech like Geiger-Müller, but can be used. So to work in a simple lab, to just detect leakage anywhere, you can carry this dosimeter. It's very helpful. You can just use it to identify the radiation level, and then Geiger-Müller is the most accurate one. This is the one they will carry. They will carry to detect radiation anywhere. And then this is the Geiger-Müller tube. You can see the Geiger-Müller tube. You will know from the Geiger-Müller tube, once the radiation enter, when the radiation enter, all right, through the mica window. This mica window is made to be a very thin layer so that even alpha can enter. I know you can question me, sir, alpha can be blocked by paper. So how can alpha enter? It's very tiny. Alpha also can enter. If alpha cannot enter, scientists knows for sure if there's a lot of beta and gamma ray, there's a high possibility alpha also is there. Sorry, alpha also is there, right? Okay. So once the emitted radiations enter through this mica window, we know what will happen here. The next thing what will happen here is that the ions are formed inside here. So at the positive electrode, beta will be discharged. At the aluminium tube, alpha will be discharged. And helium, neon, and argon gas at low pressure will be ionized by the gamma ray temporarily, for a while only. I know they are very stable. They will try to remain neutral, right? But once they ionize, they will be discharged also temporarily, and current flows in the system. So very high voltage current we carry, and inside there got transistor. With the help of the transistor, we can amplify the current, so we will see the level of current flows in a unit time, maybe per second, maybe per minute. As we see that, we will identify what is the amount of radiation detected. This is a very helpful device. Very helpful device, bigger molecule. Only with this device we can detect exactly berapa banyak quantity of radiation can be detected. Very helpful. Okay. Beside this device, we have a spark counter. This is how a spark counter look like. This is a simple. You all got class after this. Give me 1 more minute. Okay. See here, you will carry the radioactive substance here. See this guy holding. All right. So this system is only able to detect very strong alpha and sometimes a bit strong beta. That's all. This one only can detect alpha and beta, very strong only, because you see gamma is neutral most of the time. So when you bring this radioactive element here, the guy is carrying here, see here, see this one is connected to positive and negative terminal. Positive and negative terminal. So the current, this whole area, see up one, will have a lot of strong cathode anode. So when alpha or beta enter here, they will be discharged or reflected. So if this is a negative terminal on the upper surface is negative. So if alpha comes in, alpha will be discharged. So small current will flow. So we can see the reading here, a small current flow. And it will create sound. Spark counter will have sound. You see YouTube got videos. It creates a sound like a normal clicking sound, like that. Okay. And if let's say beta enter, if beta able to enter through or reflected, also got sound. If able to enter through, beta will be discharged by the positive terminal. All right, that's it. Any question?